Right, class. Hello, everyone. Hello, Justin, Rachel, Jason. Morning, everyone. We are back finally, and before we start, I have a new system, so I want to make sure that everything is okay on your end. So I would like to know if the video is okay, if the audio is okay. Also, let me change to this. Is this okay? You can write on the chat. All right. Okay, perfect. If there are any... Okay, thank you. So, is there any issues? I'm not expecting any issues. This is an assistant, so, but is there any issue during the meeting? Just let me know, okay? All right. I think we are ready to start. Were you able to watch the recording for Unit 11? Let me close this. Okay. So, Unit 11. Okay. And you will see, so Unit 10, we work with exponential functions. Okay, so we treat now, let me change this because I'm writing. We introduce the exponential function as operators. Okay, we are going to treat them as operator because our goal is to learn how to solve exponential equations and logarithmic equations. Okay, so Unit 10 was exponential equations. The inverse of that is the logarithmic functions. That Unit 11. Now we are going to combine both, and we are going to be working with the two at the same time. Okay. Most important of today is to get all the properties. To remember, we are going to be working with all those properties from exponential logarithmic functions to solve equations that have both operation or both functions. Okay. So we're going to start with a recap of what we have studied on the previous two units, and then you are going to see how we are going to use the properties on the exercises. All right, so we have we know. Oops, let me change this. Let me maybe this a little bit. So we have exponential functions. All right. And we know that the inverse of the exponential functions are logarithmic functions. Okay, they are inverse to each other. Okay. So between these two functions of two operators, the weird one is the logarithmic function, because now we are working with numbers, not as we are used to work with, or with the format that we are used to work with. Because the exponential function here, I just using the base and the exponent. Okay, so the constant factor there, c, is equal to 1. So this is a format that we are used to work with because it is an exponent. With logarithmic functions, now we are going to be introducing this new notation, log, so referring to logarithmic function, okay, where a is the base of the logarithmic function and x is the argument or the input of the function. So let's call this one the parent functions. And with this, we got the key points. So here we have -1 and 1 over the base. 0, it is the initial value. A raised to 0 is just 1. And then +1 and the base is just A. Okay. We know that exponential function have horizontal asymptote, and that is y equals 0. That's the equation. Okay. The log base A of x is just the inverse function. So we don't need to think too much of what will be the key points. We just need to flip what we have here on the left side. Okay. So -1, 0, and 1. This is a technique that you might want to use when you are looking for the key points of the logarithmic functions. A log, like I said, is a weird function or operation. And usually working with finding those points with the log is a bit complicated depending on the value that we are getting. So sometimes it is good just to go and work with the exponential function that relates to that logarithmic function, calculating those key points from the exponential function, and then just flipping the coordinates. So the x goes to the second entry and the y goes to the first entry to get the key point of the logarithmic function, because they are inverse. Okay, so we can do that because they are inverse to each other. All right, so here the input will be 1 over a. Here it will be 1, and here is going to be just the base. So we flip the horizontal asymptote to a vertical asymptote, and the equation is just x equals to 0. So here, then, if I can extend this, the domain for the exponential function will be all the real numbers, so from -infinity to +infinity, and the range, okay, this is important. The range here is going to be from 0. We are not going to include 0 to +infinity. Okay, that is why we have, or you can see the relationship between the horizontal asymptote and the range. Okay, since a is a positive, the value of the base is positive, we are going to have always, we cannot get 0 or negative values unless we have a shift or a subtraction in the output. But in the parent function, we will never get, from the parent function, we will never get a value of 0 or a negative value, because yes, we're not going to get a negative value because of the exponential operation. Well, if we use -x, we are going to use that negative in the exponent, and having an exponent, a negative exponent, it doesn't turn the value into negative. What it does is that it flips the operation, so we will get the reciprocal of the base. All right. So how this domain and range relate to the logarithmic function? Well, they are inverse. So now the domain of the logarithmic function is from 0 to +infinity, and the range is going to be from -infinity to +infinity. Okay. Again, you can see the relationship between the vertical asymptote now and the domain of the logarithmic function. The shape of their graph when a is, let me start with from 0 to 1. When the base is from 0 to 1, we will have a decreasing behavior, okay, knowing that the vertical asymptote is here, the horizontal asymptote is here, sorry. So that's the horizontal asymptote. Okay, when a is greater than 1, so we will have an increasing behavior. You will see how we will use decreasing behavior and increasing behavior on the next unit, because on the next unit we are going to start working with real life problem that involves exponential function. Okay, so this decreasing and increasing, or the growth factor, will make more sense on the next unit. Also, this is very relatable to biology and economics. Okay, if you are interested on those branches or on those area, you will be using this type of graph or operations later on those classes. Okay, so decreasing when a is between 0 and 1, and increasing when a is greater than 1. Okay, but this is also, we can do the same for the logarithmic function, because the logarithmic function is just inverse. I don't know why I can't do that. Can I flip this? Okay. Okay. Okay, this is the difficult part, but here we have this. Okay, careful with this shape, because they seem the same right now. Okay, the only thing that it is different between the shape of the when a is between 0 and 1 from the exponential function. The only difference between these two shapes here that we are seeing here is the asymptote. For the exponential function, we have a horizontal asymptote. For the logarithmic function, we have a vertical asymptote. Okay. So this one goes here. And when a is greater than 1, the shape right now, I don't think it will be so important as when we work with transformation of functions. Okay, we are not going to use too much the shape here, and let me put this in this. The correct one is this one. But this is just good to know that the shape of the logarithmic function are going to be like this. Okay, so those are the shapes of the functions. What else? All right, the most important part for today is the properties of each function. For the exponential function, we are going to use the exponent laws, or the law of exponents. Okay. For the logarithmic function, what we are going to use to solve logarithmic functions is the following question. Let me copy and paste this, because this is what we need. So log base a of x is asking for the following. What power of the base a give us their argument x. Okay, so let me change a few colors here. So the base A and the argument. Okay. So what is this question? This question is what the logarithmic function will, or what we are going to calculate with logarithmic function. Okay. An example: when we are adding two numbers, the operation of the plus sign is asking us what is the sum between these two values. Okay, and so hence we get the result. Okay, so here log base a of x is asking for what power of what power of a, sorry, what power of a give off the argument x. A concrete example: log base 2 of 8. What power of 2 give us, okay, what power of 2 give us the argument 8? Okay. What is the exponent that we need to put on top of 2 to get a value of 8? Okay. And that is 3. Okay. So that is what we are getting, or what that is how we calculate the log base 2 of 8. What is the power of 2 that gives us 8? You will see that if we use this example, give me a moment, just sorry. Sorry about that. So log base 2 of 8 is equal 3 because 2 raised to the power of 3 is equal 8. Okay, so when we are calculating a log or a logarithmic function, what we are looking for is the exponent that we put on the base to get the argument. Okay. All right. So properties. What are the properties that we are going to be using to solve equations that have logarithmic functions and exponential functions? From the previous unit, I believe unit 10, we learned the property of if we have a raised to the x equal a raised to the y. Okay, so we have an equation, exponential equation. On both sides we have the same base. The exponents are different, or at least the representation of those exponents is different. So we have x and y. We can conclude that x is equal to y. Okay, this is a property that we use to solve equations in unit number 10, when we find first a common base between both sides of the exponential equation and then use this property to conclude that the exponents are equal. right? I told you that I'm going to show you why is this, why this property is true, but first we will need to learn about some properties about the logarithm function. This is a table that you have on the worksheet of the day. Okay, and this is something that you want to remember. Okay, this is very important because you will see how we are going to use this to solve those equations. All right, the first one. When we have log base a of 1, what is that result? This is the important part here. This is the question that I just posed before. What is the power of a that gives off the argument of 1? Okay, what power of a give off 1? Okay, what is the power of a that give off equal 1? You need to remember that every time we raise a number to a power of 0, we are going to get 1. So that is that property. Every log base a is representing any number here that fits on the base of the logarithmic functions. A base a of log base a of 1 is equal to 0 because a raised to the power of 0 is equal to 1. Okay, so the power of a that gives us 1 is 0. So the example that we have here, log base 7 of 1, this is equal to 0 because 7 raised to the power of 0 is equal to 1. Log base a of a. Okay, this one is important. We are going to use this property to cancel. Okay, to cancel bases on the equation. Okay, so this one is important. I'm just going to put the word here because we are going to use that one to cancel some bases on the equations. Okay, so what is the power of a that give off a? Well, a raised to the power of 1 is equal to a, so this is equal to 1. Okay, so log base 7 of 7 is equal to 1 because 7 raised to the power of 1 is 7. Ln is the same as log base e. Okay, remember e is a rational number similar as pi, so we use e to represent that irrational number. So e raised to the power of 1 is equal e, so that means that log base e of e is equal to 1. This one might be confusing because the way it is set up, but once we see an example, it will be easier to see it. All right, so here we have log base 2 of 8. What is the power of that gives off 8? That is 3 because 2 to the power of 3 is 8. All right, so 8, because of this, that means that 8, we can write 8 as just using the number 8, or we can use an exponential expression, 2 raised to the power of 3, right? So that means that we can substitute this 8 here with log base 2 of 2 raised to the power of 3, or 2 cubed, okay? So what you are seeing here, the argument is just 8. It's just that we are using a different representation of that number. Well, this go and it is equal to 3. We just take the exponent and we put the exponent here in the right side of the equation because it's the result of this logarithmic function. Okay, so in a way you are seeing that we are like canceling the log or the logarithmic function with the base of the argument, and we are just taking the exponent. Okay, this one is another one that is going to be important because we are going to use to cancel or to bring down. This one we are going to use to bring than the exponent. Okay. So log base a of a raised to the power of r is just r. And again, the question here, the phrase that is in the middle is asking, or is the answer for the question, what is the power of a that gives of a raised to the power of r? So here, very straightforward. We have the same base for the logarithmic function and the same base for the exponential argument. So we just take the exponent and we put it on the right side. Okay. Another one that is confusing, but this one is another one that we are going to use to cancel. Okay. So let me give you an example of this first, and then we can continue with the table. So what we have the log base a, is a raised to the power of log base a raised to the power of log base a of m. Okay, so we want to know what is the value of this. So what we know that this is the power you say color, the exponent. Let's focus on the exponent. Okay, let's focus on the exponent. The exponent says the power of a that give us m. Okay, since we are working with variables, so we don't have an exact number here or an exact value. So what I'm going to do, I'm going to use a variable to represent the power of a that gives of m. Okay, so I'm going to use n to represent the power of a that gives of m. Okay, n is the power of a that gives of m. So that means that if I take a and erase it, to the power of n, okay, a raised to the power of n, this is equal to m. Okay, let me give you a concrete example. Three and 81. So log base 3 of 81 is the power of 3 that gives us 81. That is 4. Why? Because 3 raised to the power of 4, it is 81. Okay, so that's what we are doing here. Okay, so that helps us to understand now the exponent log base 8 of m. Now, let's finish this part. When we use log base of m as the exponent of a, what will be this? Well, we know that log base a of m is equal n, and n is just the exponent of a that gives of m. So at the end, this expression is just equal to m. So in a way, it's like canceling the base of the exponential as expression here with the logarithm function in the exponent, and just taking the argument and putting it in front on the right side of the equation. Let me give you an example. So 3 raised to the power of log base 3 of 81. Okay, log base 3, 81 is equal to 4, so this is the same as 3 raised to the power of 4, but 3 to the power of 4 is just 81. So it's like canceling this 3 with this log base 3 and just taking the down the argument. Okay. So this property here says this is equal to m because a raised a raised to the power of log base a of n is just m. So this is m. Okay, and here this is m and m. Okay. Again, I just discussing the properties. You will see how we use this property. It will make more sense when we start working with examples, right? We get back to this when we are working with the examples. There is one more property that is not on that table, and that it is important before we get to the product and quotient property. Let's call it the power property of the log. Okay. So if we have log base a and the argument has an exponent, we can bring that exponent down as a factor of the logarithmic function. Okay, but see that now the exponent of the argument is no longer there, because we use the exponent and we put it in front of the logarithmic function as a factor to the value of log base a of x. An example. Okay, log base 5 of x squared is the same as 2 times log base 5 of x. Okay, this one is an important property that we are going to use as well to modify the equations. Okay, let me see if there is one more. We have one more that is very similar to the one that we have here. So if we have log base a of x equal to log base a of y. Okay, so the important thing here, is that the a are the bases. The bases are equal. So we have a on both. We have logarithmic function on both sides of the equations with same base. So we can conclude that x is equal to y. Okay. Okay. Before we go to product and quotient property, why this is true. And you will see that if we use properties that I have just shown here on the right side, properties of the logarithmic function, we can see what's happening, or we can prove why this is true. We are going to use this property here, the one that we are going the one that we use to cancel, and we are going to use the power property. Okay, that's the two properties that we are going to use. So the inverse operation of the exponential operation is the logarithmic function of the logarithmic operation. So in order to cancel the base here and bring down the exponent, we can do the following. We can put log base a on both sides of the equation. This is very similar to when we subtract, when we want to cancel, for example, if we want to cancel 2 from the left side, we use the inverse operation of addition, which is minus 2. Okay, and that way we can solve for x. Okay, so what we are doing here, we are using the inverse operation. So we have an exponential equation, so we use a logarithmic function to cancel the exponential operation. Okay, then I'm going to use the power property of the logarithmic function, so that brings down the exponents. The exponent here are x and y, so I bring down x as a factor, and also I do the same for y. Okay. Using the second property that we have here, log base a of a is just 1. So we basically cancel these 2 because that's equal to 1, and what is left is x equal to y. And that's how we prove that this property here is true, right? So if we have an exponential equation, both sides of the equation share the same have a common base, or share the same base of for the exponential operation, then we can conclude that the exponents are equal. Okay, and this here is the proof of that. Okay. Going back to this, the product property and the quotient property, this one also are going to be important when we want to simplify logarithmic equations, or when we want to like expand logarithmic functions or expressions. So what is the deal here? We have a logarithmic function, and in the argument we have multiplication. We have two products, m and n. So when we have a multiplication here, we can separate those two factors, okay, and use them as argument of individual logarithmic functions. Okay, the important thing here is that we are going to add. If they are being multiplied, if we have a multiplication in the argument, we can separate those factors into individual argument for two different for two logarithmic functions, the base need to be the same. The base stay the same, which is a. So we can separate that into two logarithmic functions with the same base, and we add them, and the value is going to be the same. For division, it's the same. Careful here, because now we have a subtraction. That means that one of the terms here is negative. So for put this here on the top. For when we have a division in the argument, we can separate as well the two components of that division or fraction. So log base a of m minus log base a of n. What's important here is that the denominator is the one that goes and it's the one that is become negative. Okay, careful here. So denominator is the one that will become negative. Okay. Denominator. But that's enough of theory discussion. Now, let's see how we are going to do this. How we are going to use all these into their exercises. Okay. Any question before we start? Right? Okay. Careful with these exercises. They are very infamous. They are very easy, but a lot of my past students got this wrong every time. Okay. So what we are going to do? We are going to turn the exponential equation into the logarithmic equation. So basically what we are doing is looking for the inverse function of this, okay? We don't need to go through extend algebraic process here. We just need to identify the key component of the equation and then use it on the inverse equation or inverse operation. So we are going to rewrite an exponential. A is exponential. We are going to rewrite as a logarithmic equation. So let me put this here. So from exponential to log. And what we have is e raised to the power of 2 equal y. So what you want to do here, you want to identify the base. You want to identify, in this case, the input, which is the exponent. If in an exponential equation or function, the input is on the exponent, and what is the output? So the base is e, the input is the exponent is 2, and the output is the result, so y. We turn this into a logarithmic function. So we use log, we take the base is e, and now remember that the logarithmic function is the inverse operation or the inverse function of the exponential function. So we swap the input and the output. So the output now becomes the input of the logarithmic function, so the argument, and the input of the exponent, the exponential function, becomes the output of the logarithmic function. Okay, and that's how you turn the exponential equation into a logarithmic equation. Question with this? this. Okay, because the base is e, we can simplify the logarithmic function as ln. Okay, that is just a simplification of log base e. Natural log of y equals 2. Okay. The second exercise that we have here, we need to go from log to exponential equation. And we have ln of x equal 4. And we are going to repeat the same process. Identify the base, the input, the output. The base, ln, is the same as log base e, so the base is e. The input is x, the output is 4. We do the inverse. We start with the base, the output becomes the input, e raised to the power 4 equals to x. That's how you reach the conclusion. Any question? Okay. On this exercise, we are going to use the properties of the quotient, the product, and the power property. Okay. So A, yeah. Okay. So A. So we have log base 7, log base A of 7 minus log base, did I say 8? Okay. Log base 9 of 7 minus log base 9 of 8 equals log base 9, and then we do not know the argument that goes here. Okay, so what are you going to do here? So you are seeing that in this equation, the left side of the equation, you have two terms. Those two terms have logarithmic function, and the logarithmic function share the same base, which is 9. Because we have the same base and we are subtracting both terms, we can use the quotient property here. The quotient property, what it does is that it simplifies this subtraction into just one logarithmic function, where we take the positive term, the argument of the positive term will become the numerator of a fraction that is going, or the numerator of the new argument. So the new argument will be composed based on the two original arguments, so 7 and 8. So the argument of the first term, or the first logarithmic function, is 7. That 7 will become the numerator. The argument of the second logarithmic function is 8. The second logarithmic function is the one that is in the negative term. So A will become the denominator. So this is 7 over 8. Okay, that is the argument. So the answer here is, what is missing is 7 over 8. And in this exercise, we use the quotient property. Okay. B. Log base 7, we don't know the argument of that term, of that logarithmic function. Here we have log base 7 of 4 equals log base 7 of 12. Okay. So we do not know the argument of the first logarithmic function. So what I'm going to do, I'm going to use a variable. Okay? So using a variable allows me to work algebraically here without knowing that exact value. So we have on this equation two terms on the left side. Those two terms are functions, contain functions with the same base, logarithmic function with the same base. Because we have a multiplication, we can use, because we have an addition, we can use the product property. So now it will be log base 7. So now we combine the two arguments into a multiplication. So the argument, both arguments are going to be, and here it doesn't matter the order because both are positive. What we are going to just to take the arguments and we are going to put them into a multiplication, x times 4. This is equal to log base 7 of 12. Okay. So we need to go further because we are looking for the value of x. But here we can use the property where we have an equation. Both sides of the equation have a logarithmic function. They share the same base, 7. So we can conclude that x times 4 equals 12. And we know how to solve this. Here we just need to divide both sides by 4. And we get x equals 3. So what was missing is 3. Any question on this one? Okay. So C is log base 3 of 27 equals, so we are missing something here, log base 3 of 3. Here we are going to use the power property of the logarithmic function. How are we going to do that? So we are seeing that on the left side we have an argument of 27. Clearly 27, it is a power of 3. So we know that this side here, it will be equal to 3. Okay, so we can calculate that, but we are not calculating here the logarithmic function. We are looking for the missing part on the right side. Okay, so you might be tempted just to put 3 here, but if you put 3 here, you might want to, well, you can continue and figure out with other properties the value that is missing here. But here, what I want you to do is to use the power property of the logarithmic function. 27, we know that 27 is equal to 3 to the power of 3. So if I substitute 27 with 3 cubed on the right side, okay, we are almost there. Because if we remember from the power property of the logarithmic function, the argument has an exponent, but that exponent can become a factor in front of the logarithmic function. Okay, and that number that was missing, it was that exponent, the number 3. Okay, so we solve this exercise, this equation, by using the power property. Okay, yes, you could have used, you could have calculated log base 3 of 27, that is 3. And you can also notice that on the right side, log base 3 of 3 is just 1, so you can cancel out that. And that's another way to get the value of 3, okay? But now you have seen how we can use also the power property. Written work of those exercises. Let me know if you have any questions. Okay. Again, here we are going to use the property of the logarithm. Here we want to evaluate. So we want to know exactly the value of this expression. So let me put them here so you can see it better. 2 log base 3 of 4 minus log base 3 of 48, and what's the value? Okay, when you see the word evaluate, that means that we need to reach a value. Okay, so we need to calculate the values here. So we need to use the properties here, because without calculator, how are we going to be able to evaluate this expression? So we have two terms. We have a subtraction and we have two logarithmic functions. They share the same base. So you want to use then the quotient property. The problem here is that the first term is not in a way that we can use the quotient property. Very careful here. To use the quotient property, let me go back to the worksheet of the day. The detail here is that you can see that from the quotient on the property, focus on this side, there's nothing there. So there is no factor in front of the logarithmic function. The problem here is that the first term has a factor of 2 that is being multiplied by that logarithmic function. So if you want to use the quotient property here, because there's a subtraction and we have a common base for the two logarithmic functions that we have there, then we need to find a way to put the first, or to eliminate in a way, or to modify this so the first term is not being multiplied by 2. So what can you do here? Is there something that we can do to modify this so then we can use the quotient property? Do we have another property that relates a factor in front of the logarithmic function?
Can't you move the 2 to the exponent of 9?
This, of 4. This is 4, sorry.
Oh, yeah. 4, sorry, yeah, 4.
So we want to use the power property of the log. So I'm just focusing on the first term. So you are going to take that 2 and it's going to be the exponent of the argument. Okay. So using this, now we have the following: log base 3 of 4 raised to the power of 2 minus log base 3 of 48 equals, that is something that we need to evaluate now. Okay, so let me evaluate 4 raised to the power of 2, that is 16. And now we can use the quotient property. Quotient property says that we can simplify two terms with logarithmic function, with the same base of logarithmic function, into just one logarithmic function. Okay, so in this scenario, we are going from right to left. Okay, so we have two terms, common base within the logarithmic functions. So we are going to use the two arguments and we are going to put them in a fraction. So this is going to be log base 3, and the detail here is which argument goes in the numerator and which argument goes in the denominator. By the subtraction, you can see that the second term is the one that is negative. So 48 goes in the denominator and 16 goes into the numerator. Okay, we still haven't reached our goal, which is getting the exact value of the logarithmic function. You will see that 16 over 48 is just 1/3. And now we are dealing with this logarithmic function. What is the power of 3 that give us 1/3? Okay, so how would you answer this question? Can you answer this question without calculator? Is there some exponential laws or laws of exponent, or is there any law that will help you to evaluate this? Look what we have here. We have a log base 3, and in the argument we have 3 again, but this time 3 is on the denominator, so we have 1/3. So is there a relationship between 3 and 1/3? Do you think it is possible to evaluate this without calculator? If so, do you know what number goes on the right side? Yes, it is -1. Why, Tristan? Because if we raise 3 to a -1, what we do is what we just get is the reciprocal of 3, which is 1/3. So what is the power of 3 that gives off 1/3 is -1. So that goes here. That is what we are going to evaluate. All right. Okay, so written work for this one. This is not written work. This is not written work as well. So written work will be this one, this one, this one, this one. Okay. Any question with this one? All right, so let me just copy B. So B, E of 3 plus so we need to evaluate this. Can you solve this in 2 steps? So if you have 2 steps only to solve this one, what will be those steps? Or at least what are you seeing here that you can use to reach our goal? I like that. Yes, we can use the product property. But I don't think that using I think if you use the product property, you will solve this in 3 steps. I want to solve this in 2 steps. How would you do that? What are we seeing here? Let's just focus before on the properties. Let's focus on what we are seeing here. Do not do that, Tristan, because then you will be creating a new exercise. You don't need to set something to 0 here, because we are on the right side we have nothing. Okay, here we have nothing, so there's no way we are not going to solve for a variable. It's the same base. Correct, Tristan. Yes, it's the same base. So at the end, it's just, this is equal to 10. This is equal to 10. So let me give you the 2 steps. The first one, I will use, you can use the product property. You can combine these 2 logarithmic functions into one, and then see that you can cancel e. But if I use the product property, I can bring down the exponents. The product property, the power property, sorry. If I use the power property to bring down the exponent as factor in front of the logarithmic functions. Okay, and I want you to focus on L and E, natural log of E. What is the value of natural log of E? What happened with this logarithmic function? Okay. Ln of E, remember, is log base E of E. What happens when the base and the argument are the same? What is the value when the argument and the base are equal? Cancel, because the value is just 1. Because we are in a multiplication, we are just going to cancel them, because 3 times 1 is just 1. 7 times 1, 3 times 1, I don't know what happened with me today. 3 times 1 is 3. 7 times 1 is 7. So we cancel because we are using them in a multiplication. So this is not part of the written word. So 3 plus 7 equals 10. Okay. If you use the product property here, the product property, yes, not the power property. I use the power property. So power property of the logarithm. Product property. So to use the product property, you will do E q times e raised to the power 7. You use the law of exponent here, log natural log of e, so 3 plus 7. Okay, because the same base, we are multiplying the exponential expressions. E raised to the power of 10. And from here, you can do both things. You can just put 10, or you can use the power property. You put 10 in front of natural log of e. Natural log of e is just 1. So this is equal to 10. Okay. Either way is correct. Any questions? All right. Okay. So now we are going to start seeing, if I'm not wrong, from now on, yeah, we are going to start working with equations. So what we just saw, what we had just saw is the properties, how to use the properties in specific scenarios. Now we are going to be working with equations. Okay, and when we are working with equations, here the goal is different. It's to find the value of the unknown variable. So we have an equation here, and the problem is that our unknown variable is confined in the argument of the logarithmic function. So we have 5 times, let me write this better because it could be confusing. So what is the strategy? Okay, the strategy here is going to be always the same. So this is the part that is important. This equation is fairly easy to solve, but the strategy that we are going to use here is the same strategy that we're going to use on the rest of the equations. Okay, so this part is important. The first step will be, since we have the unknown variable in the argument of the logarithmic function, and so we need to solve that equation for that variable, what we need to do is to isolate the logarithmic function entirely in one side of the equation. We have only one logarithmic function in this equation. So isolate. Yeah. Isolate the log function. Okay. So how are we going to do that? The first thing I want you to remember is that ln, when we use logarithmic functions, that is another way to write values. Okay, so what we have here this highlighted in yellow, that's just a value. That's a factor. Okay, so I'm going to substitute just for a moment ln of x with a variable. Let's use a, or maybe let's use m. All right, focus on this equation. Here, that is just a linear equation. Okay, m is the unknown variable. Can you tell me what step you need to do to isolate m on one side of the equation, to leave m alone in one side of the equation? What are those steps? What you need to do to isolate or to solve for m? Subtract by 6. You will subtract by 6 on both sides of the equations. And then divide by 5. Then you can see that m is just negative 2 over 5. Okay? Why we were doing this in the linear equation? Just to show you that you are going to treat the logarithm function as just another number or factor in this case. Okay? Don't get intimidated by the notation of the logarithmic function. You see log base something there. Well, that's just a number. Okay? We don't know the exact number, but we have the calculator there for that. But we are not interested on the exact number. We are interested on what we can do here. Okay? So what I'm going to do is just to substitute m with the logarithmic function. Okay. So this is get canceled. So the next step will be, now I can drop the parentheses. The parentheses, I use the parentheses sometimes just to help me to visualize or to separate the factors, okay? Okay, so now that we have changed or we have modified the linear equation into a logarithmic equation now, because this is just a logarithmic equation because we have a logarithmic function on one side of the equation and the rest are on the other side. Okay, so we are focusing now on the logarithmic function. How we do this? So the rationale here is what we are going to do is going back to the question. What is the power of e? The base of this logarithmic function is e. What is the power of e? So let me isolate. So we isolate, and then now we are in the second step. The second step is we are going to turn, move this here. So this is the second step. I'm going to name second step just in a moment. Here, what we have from this expression, we can get this following. What is the power of e that give us x? Well, the equation right now is answering this question. Okay? So what we want to do, or how are we going to use this question to solve our problem? If you turn the logarithmic equation into an exponential equation, you will see that you have e raised to the power of -2 over 5 equals x. And that's what we are looking for. Okay? Let me go back here. So in the second step, we are going to cancel the log function. The rationale of how we can cancel the logarithmic function, it is here on the core of the logarithmic function. What is the power of e that gives x? The problem is that x here is the unknown variable, but we are going to treat that variable. Well, that variable is the argument, so we are just going to use the property of what we know about the logarithmic function to figure out the value of x. Answering that question, we can turn the logarithmic function into an exponential function, or into an exponential operation, or exponential operation. And what we have here on the left side, I know that it doesn't seem like a number or a value, or it doesn't see like a value as we are used to see values, but that's a value that we can calculate. That's e is representing a value raised to the power of -2 over 5. We have our calculator. We don't need to have a hard time figuring out the exact value of that. Okay, I'm going to get back to that part of the calculator just in a moment, but I want to now show you how we do this step in an algebraically way. So if I am working on the test, I'm not going to write the question, this question. This question is going to be on your mind, and you're going to use that question to reach the goal. But you can do the following. Similarly, as we can put logarithmic function on both sides of the equation, we can do, or we can put exponential operation on both sides of the equation. How you do that? Well, you take both sides of the equation, the left side and the right side, and now you will use them as exponents of the base of your choice. The base here that we are going to use is e, and you will see why. So let me focus here. Okay, so what we did, we took the two sides of the equations and we put them in the exponent of the base e. So we add the exponential operation on to both sides of the equations. What is the importance of this? Well, we have a property. And what property is that one? This property here. So when we have focus on the left side only, so we have an exponential operation. The base is e. In the exponent of that exponential operation, we have a logarithmic function, and the base is the same. Both bases, the base of the exponential expression and the base of the logarithmic expression, which is in the exponent, are the same. So basically, we cancel these two, and we bring down x. We cancel these two, and we bring down negative 2 over 5. Wait, I did something wrong here. I don't know why I put natural log here, but that's not the case. It's just e. Okay, and that's how we reach the answer. Okay, my bad here. I put ln for no reason there. Okay, that's incorrect. It's just taking the size of the two parts of the equation and using them as exponent of the exponential expression there. Okay. Okay. So that's how we reach the goal. Okay. The exercise is asking us to give an approximation of this value. And how would you do that? Let me find those things here. Where are you? Okay. I would recommend to you to use the calculator that you have on Desmos, on Alex. So on Alex, you will do the following. This is how I solve it. E to the negative to 2 over 5th, a or 2 over 5 is the same because the exponent is negative. I just use 1 over e raised to power 2 over 5. Okay, this is something very weird to write down, or very difficult, very complicated sometimes on some calculators. The benefit of using the calculator that you have on Alex is that you can see exactly what you are writing, and you can use your keyboard or this key here. Okay, it's a bit more friendly, this UI here. So what I did is I just click first on 1 and then division, and that brings 1 over something, and it gives you the option here of square. So then you can use your mouse and click there. When I click there, so I wrote this e. So what I did is just click on e raised to the power of x. And then to make sure that I'm writing on the exponent, I click on open parentheses, then 2 divided by 5, and then closing parentheses to make sure that all that stay on the exponent. Okay, and that's how you get this. And then just clicking enter, and you can see that I can highlight this or select this with the with the mouse and copy and paste it. Okay, this is the value, so you will copy and paste it, and you need to round to the nearest hundredth. So nearest 100 means 2 decimal places, so you are going just to copy 0.67 and then paste that as your answer. Any question with this one? Okay. So now we have a logarithmic equation. Our variable is x. The number is x, and it is confined in this logarithmic expression or in this logarithmic function. So our goal here, right now we have our equation isolated, or our logarithmic function is isolated in one side of the equation, is on the left side. Now we want to eliminate that logarithmic function. So we are going to cancel that. So 2 ways to do this. You can use what is the power of 2, that give of the argument. The argument is 3x minus 3, and the answer here is 4. Okay. If you want to do like a complete algebraically expression here, so you are going to take these 2 steps are the same. Okay, they are just equivalent steps. Okay, these 2 steps are the same. So this is going to be 3x minus 3, 2 raised to the power 4. Okay, so on the left side, I just answer the question. What is the power of 2 that give of 3x minus 3? Obviously, 3x minus 3 is something that we don't know exactly, but since we have an equation where the output, or on the right side we have 4, we can use that information and put that to create an exponential expression that will help us to finish this exercise, or to solve this exercise. Okay, if you do not like that using that question and you want to see us more algebraically work, well, take both sides of the equation and use them as exponent of an exponential expression. Here I will choose the base of my exponential expression the same as I have in the logarithmic function. Why I do that? Because now I can cancel this and can bring down 3x minus 3, and this is just 2 to the power of 4. Okay, both are the same. Okay, either way is going to be okay. You will find these steps more in mathematical textbooks, but here, since we are working more laying more on the properties, you can just go straight forward and get this. Okay, so I'm going to continue on the left side, and this is an equation that you can solve, because now this is a linear equation. This is 16 here, 3x minus 3. So what you do here is to add both sides, so 19 3x, and then divided by 3x by 3. And that's your value. Okay, any question on this one? Okay, so I'm going to give you a few minutes, so let's take a 5 to 10 minute break. Try to do this one to see if you are getting that strategy of isolating the logarithmic function, canceling the logarithmic function, and then solving for the variable. Okay, so I'm going to give you, can you see this well? I think so. It might be Let me put it here. Negative 6 log base 4 of 5x equals negative 12. Okay? So try to solve this. We give you, we are going to get a break, 5 to 10 minutes. Try to work that. There's exercise in that break. Let me know when you have a question, post on the chat. I will get back here in 10 minutes, okay? Any question before we go to a break? All right, so let's move this.